I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray that you be with us today. Help us to, again, just glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. Okay, so I want to talk about the wave equation today. And, in a perfect world, I would rattle off a derivation of it for you here. Actually, first I should just ask, did you guys see a derivation? Yep. Oh, you don't need to zoom in. You're fine. I think I got it at the right kind of, you're fine, right kind of zoom level. Oh, no, thank you. You're right. Goodness gracious. That should be good. It's the thing on the top, okay. But yeah. Okay, so how many of you have seen a derivation? Oh, let me write down the wave equation to start with. What is the wave equation? Is partial squared y partial x squared equals to 1 over v squared partial squared y partial t squared. So this here is the so-called wave equation. So how many of you have seen a derivation of that in Physics 231? Did you have homework problems where you were given like sines or cosines and asked to show that it solved this equation? Maybe? It was a long time ago? All right, well, in that case, I guess I probably should spend 5 minutes trying to derive this thing for you, huh? So suppose you've got a string, all right? And if you zoom in on like a little segment of it, like this one, all right, then basically the motion of that string is predominantly from the tension in the string, right? I mean, yes, there's also gravity, but the distinction between gravity on one part of the little segment and the other part is not so much. So the dominant thing here, as long as the vertical displacement isn't too severe, right? I think something like this. If we blow up that little segment, we should be able to understand, this wave equation. Now, so this point would be at like y of x, y of x, all right. And this one over here would be at, I'm sorry, labels. So this is at x comma y, and this over here would be at x comma, I'll get it eventually, x plus delta x comma y plus delta y, right? And let's see here. And then we can basically just look at Newton's second law on this little bit of string, right? So what's happening is you've got sort of the tension force this way and the tension force that way, right? And so let's see here. So tension like so, and over here like so. Now, what direction should these be in? Right. Yeah, tangent. It should be in the tangential direction to the curve. So this one should be at slope, partial y, partial x at x plus delta x, right? And this one should be, the slope should be what at this one? Partial y, partial x at x, right? Let's see here, and how to get this. So we can write, we think of this basically, excuse me, think of this line segment as like a little mass m, And just write Newton's second law in the y direction for this. What would that look like? Let's see here. Partial squared y, partial t squared. The reason I write partial there is because y is a function of x and t, generally speaking. So that would be the acceleration, right? ma, in the vertical component of it, at least. And that should be equal to the net force in the y direction, right? But the net force in the y direction is what? It's the vertical parts of the tension force, right? So if I was to write, if I'm using big T as the magnitude of the tension, okay? So this is really the magnitude of the tension is the same on both sides of the string, right? We're assuming the string doesn't elongate, so the tension is the same magnitude as you go through the string. Anyway, so tension times what? Well, this one here would be partial y, partial x at x plus delta x, right? And then the other force over here would be minus partial y, partial x at x, right? So, and really, this isn't m. What is this? This is really, I mean, it's m, but maybe it'd be more appropriate to call this delta m or something, right? It's a little bit of mass, you know. So this is some sort of finite approximation. But what happens is we take delta x going to 0. I mean, you can solve this, right? And this would give us that partial squared y partial t squared equals to t over, delta m, right? Let's see here, how to say this. So that's the tension, how to say that? What happens to this term over here, though, is delta x goes to 0. What's that become? We have the difference. I mean, this is partial y partial x at x plus delta x. Oh, you're right. You're right. You're actually right. So what I should write here, instead of m, I should write like the mass per, man, how to say that? Curses. You know what I should do? I'm sorry, guys. I should express this in terms of the mass density times delta x. That will be more helpful to us. So delta m is lambda times, I knew I forgot something in here. Sorry, guys. I like to take a second to think about what I'm about to say before class. I've been knee-deep in linear algebra for the last 2 hours, and now you guys are paying the price of it, so sorry about that. So now expressing it in terms of delta x, so we don't just get 0. Now divide delta x to the other side. What happens, right? If I divide delta x over here, and so, over here, gone over here, there's lambda. So I get t over lambda times what? What happens to this expression right here as delta x goes to 0? What is that? You have the difference in the partial derivative at x plus delta x minus x, right? Divided by delta x. That's the change in the derivative with respect to x. That's this thing. So that's exactly partial squared y, partial x squared. And then if I just solve this thing the other way around, there's nice extra physics in here that we can observe and appreciate, because dimensional analysis tells me that the meaning of the coefficient, right, is that 1 over v squared is lambda over t, right? So this also tells me in this derivation, I get that the speed of the wave is the square root of the tension divided by lambda, where lambda is the mass density, linear mass density of the string. So what does this say qualitatively? It says some really nice things, like the more taut a rope is, right, of a given mass density, the more tightly you stretch it, the faster the speed of a wave goes across it, right? So like think about jump rope. You know, if you have it really tight between two people, one of them gives it a wiggle, that wiggle gets to the other person faster than if it's really loose and they give it the same kind of wiggle, right? The more taut a rope is, the faster the wave goes across it. And also, it's inversely proportional to the mass density, right? So sort of the skinnier the rope is, the faster the wave, right? If you had less mass per unit length, you get a larger speed. So if you look like a wave in a chain, kind of a qualitative cousin to this, you'd expect a wave in like a chain to be much slower than the wave in something like a kite string. Yeah? Although a kite string, I probably have to start thinking about air friction and stuff. I mean, you know. No, just an All right, well, anyway, this is the wave equation, and whether or not my derivation is completely ironclad, I'm sure it's not. That's okay. This is the physics I teach here now. And so there it is. We'd like to solve this, all right? And so what I need then is a nice problem to solve. So here's the standard problem. Come on. We're going to look at least to start with here, I'll find one of these that works better. So we have y equals to y of x comma t. This is the position, vertical, right, of string at xt, at horizontal position x and time t. We're going to consider basically a string that's going from x equals to 0 over here to x equals to L, all right? And I just explained to you what the differential equation, partial differential equation that models such a thing is. So suppose we're given that y of x comma 0 is equal to f of x, right? So this is the initial shape of the string, right? And we're also given, what else do we need?
Y of 0, comma t.
What's that?
Y of 0, comma t.
Y of 0, comma t. I mean, there are different kind of boundary conditions we could think about, right? You could think about, I mean, there's sort of, these are easier to think about. The heat equation boundary conditions are a little bit more sort of removed, right? Thermal, like an ice bath or insulating. These are just easier to understand physically. Of course, you can just take the endpoints and fix them, right? So one set of boundary conditions you might look at is just the fixed boundary endpoints, right? You might fix the endpoints. You might have y of 0, comma t equals to y of L, comma t equals to 0, right? I think that's what you're saying, Zach, right? That's the one thing we could think about. We could, what else could we do? We could just, we could fix one of the bound endpoints and let the other one just wiggle, you know? You could look at that. But in addition to an initial shape, we're actually also going to need an initial velocity. So let me.
Like velocity of the wave?
Yeah. Yeah, when we finally get to the actual real, I'm going to do a general setup here for a bit, but eventually we'll get to example 8.52, where I will look at an initial shape and, but yeah, also y sub t of x0 equals to g of x. So this is kind of the generic problem. I think we're mostly, I mean, you know, this is just a brief introduction to partial differential equations for you guys, right? Ideally, you'd have a whole course in this. So you could deal with all the kinds of interesting extra stuff that goes on. If you read your chapter in Nagel, Saff, and Snyder, you'll see there's much more in that chapter than I cover. He's got stuff about non-homogeneous boundary conditions and all kinds of other fancy stuff. But I think this problem is, as I've stated, it's pretty good for us to cut our teeth on here. We're going to assume that the endpoints of the string are fixed, and we're also going to have to assume that we have an initial shape and also an initial velocity for the wave, right? I mean, think about this. If you have a string, right, and it's held in a certain shape and then just released, that's very different than if at time 0 the string is in motion and it has that shape, right? Those are two different things. Just like if I tell you that this marker is at, you know, y equals to 3 at time 0, that's very different than if it's at y equals to 3 at time 0 and it's doing that, you know? Those are different initial conditions. The same for the string. Now it happens that in example 8.5.2, this is set to 0, but it could be something else in general. All right, enough about the general setup. Let's get to it. How do you solve this problem? So we are going to assume the boundary conditions like I just wrote down, but for some reason erased. It's here. 0t equal to 0, y of, what did I say, lt equals to 0. So this is our sort of generic problem we want to look at. Okay. So we want to solve, what was it? Partial squared y. I'm going to use the other notation. So this is yxx equals to 1 over v squared y sub tt, right? There we go. What do you think our opening move is? Danica, you guess. No? All right. How about this? Y of x comma t equals to x of x times t of t. So again, we're going to assume that we can write the solution as a product of functions of just x and functions of just time and see where that takes us. So immediately that takes us to, you know, x prime prime times t equals to 1 over v squared x t prime prime. Using the same notational idea as last time. Then we separate variables. So this gives us like x prime prime over x equals to t prime prime over v squared t, right? Same as last time, function of x, all right? Function of t, so we should call this thing like minus k. So, because it has to be a constant, right? And so, lo and behold, we have to solve x prime prime plus kx equals to 0. And we also have to solve t prime prime plus k v squared t equals to 0. Yowzers. So we have traded our partial differential equation, right, for a couple of boundary value problems with ordinary differential equation boundary value problems. Now, guess what? We can translate our boundary conditions, right? So our given boundary conditions, what do they look like? The boundary conditions, again, imply, what do they say? They say that, let's see here, y of what is it? 0 comma t, which is going to be what? It's going to be x of 0, t of t, and we also have that y of l is x of l, t of t. This is for all t greater than 0. So if our time solution is going to be non-trivial, that means that we need the spatial solution to vanish at 0 and L, right? So our boundary conditions for y give us boundary conditions for x, namely x of 0 is equal to 0 and x of L is equal to 0. But then we can go back to the start of last class, this first proposition in the chapter, right? We proved last time that forces sign solutions on us, right? This says that x of x is equal to sine, I should probably say x of n of x, right? Is equal to sine of n pi x over L, where k is equal to what? N squared pi squared over L squared. Did I remember it? See, that's the bad feeling. Like last night, my son, he like cut his head open, you know, at the Awana, running around too fast. Then I get to the urgent care and they're like, date of birth. Like, dang it. It's a bad feeling when you have to call your wife about that. It's not a good thing.
You should just put them in your phone.
Yeah, I know. But then you change phones, right? I should like have some sort of cheat sheet with me at all times. Let's see here. Actually, it's a pretty good reason to get dates of birth of your children tattooed on you. Like, that might be a worthwhile do. I mean, you know?
I feel like if you put forth that effort, you would never forget it anyway.
Right, yeah. Something like that. But are you guys with me? Anyway, so this means that our characteristic value k is not free. It has to be this. And once you have that, then we can go back and solve it. So, you know, any n will do. And so going back to star, we get Tn. Well, we solve what? We need to solve T prime prime plus, what's my kappa? My kappa is n squared, pi squared, v squared over L squared t equals to 0. This says that you've got something like Tn of t is equal to, I don't know, well, see, you got more than one term here, right? You got something like, let's say an cosine of n pi v over L, n pi vt over L, plus bn sine of n pi v t over L. Remember that this n squared pi squared v squared over L squared is just the number n pi lv over, no, excuse me, n pi v over L, quantity squared, So by our usual second order constant coefficient differential equation stuff, that's the solution. And so what's in total, this implies that we should make our solution something like y of xt equal to the sum, n equals 1 to infinity, right, of a sub n cosine of n pi v t over L times the sine of n pi x over L plus b sub n sine of n pi v t over L sine of n pi x over L. This is our sort of blank template solution, I would call it. So we have not sort of painted initial conditions or initial velocity onto that yet. But there's all the freedom you need in the coefficients a sub n and b sub n to fit initial position and initial velocity for the wave. I hope you see so far that what I'm doing is almost exactly what I did last time. Very much the same argument. So what's next then, if it's the same argument? How do we fit those coefficients to the wave? Yeah.
Is your Bn supposed to have two signs in it?
Yeah. The one, there's the sign, I'll write it again over here, n equals 1 to infinity of a sub n, what did I have, cosine? N pi v t over L, is that it? The sine of n pi x over L plus b sub n sine. You notice that there's a sine and a cosine for the time solution, but there's only a sine for the space solution. That's the asymmetry, Mike. Did I do something wrong, though? I mean, it's possible. Hopefully I just wrote it down again here. Yeah.
Like to me, or it looks the same to me. It's just
Yeah, it's just I'm just taking this and multiplying by that and adding them together. Because just the product, basically, you have y sub n of xt is x sub n of x times t sub n of t. And the idea is this one alone solves the boundary conditions, but if I add an infinite series of them, I should be able to fit initial conditions through appropriate choices of the coefficients. So let's see how to make the choices of the coefficients, right? If I plug in, so the next question is how to select a sub n and b sub n. So I need y of x0 equal to f of x, right? Let's think about that. Y of x0 is equal to f of x. All right? But we can also plug in x comma 0 into our blank template. What happens when we plug x0 into the blank template? We put t equal to 0, right? What's t equals 0 do? To this, it's gone. And here, 1, right? So we have the sum n equals 1 to infinity of a sub n sine of n pi x over L. Well, we have danced this dance before. This is the same thing we came to last time to try to fit constants for the heat equation solution. And I explained to you guys, well, I tried to, that if we calculate the Fourier expansion of f of x, or previously the initial temperature, now the initial position of the wave. If we can find the Fourier expansion of f of x, then we just choose the Fourier coefficients, and that will be my a sub n's. So basically, I just say, aha, well, this can be expanded as the sum over, let's say, little a sub n, sine of n pi x over L. This is basically Fourier's theorem, where a sub n is, what was it? It was 2 over L integral 0 to L f of x sine of n pi x over L. This is the so-called Fourier coefficient. My point to you is that that's known from integration. If you give me a specific f of x, we can, in principle, do these integrals and calculate the coefficients, and as such, find the Fourier expansion of f of x. And then to figure out which a sub n's you want, what do? You just set little a sub n equal to big A sub n, and at least you got half of your solution done, right? So we calculate these, and then set a sub n equal to a sub n. Of course, we're not done. What's left? What's still left undone? What's that? Or the b sub n's, right? I don't know, when I first took partial differential equations, I really, really loved this separation of variables argument. I just thought it was so sneaky and yet easy. But it took me a long time to really accept this separate variables and say it's equal to a constant voodoo. To me, it was very, I didn't believe it at the start. I don't know, I couldn't believe it. But it's actually quite reasonable. Let's see here. Enough. I probably have erased too much already. So we also want that y t of x0 is equal to, well, it is equal to g of x, right? But it's also equal to the partial derivative with respect to t of the blank template. Right? Which is what? Pick your poison. Sum n equals 1 to infinity. We have to partial differentiate that thing with respect to time. So we get minus a sub n pi v over L sine of n pi vt over L sine of n pi x over L plus b sub n times n pi v over L cosine n pi v t over L sine of n pi x over L. All I did was I just partially differentiated with respect to time. I use a chain rule. Chain rule says I have to multiply by the thing matching multiplying t, which in this case is n pi v over L, right? So what happens when you, this isn't quite accurate, is it, right? Blank template, then what? Maybe I should put a, depending on what notation you want to use, but at the end we set t equals to 0, right? So I got to take this whole thing and plug in t equals to 0, right? I'm sorry, if you were math students, I would say you evaluated t equals to 0. But since this is primarily an engineering crowd, I will use the proper terminology. Plug it in. Let's see here. So as in evaluate, if I said to evaluate t equals 0, I might be accused of using math jargon. We wouldn't want that. Let's see here. So, so this is 0, right? And that's what? 1, right? And so we get bn n pi v over L, right? Times the sine of n pi x over L. Well, this is a little bit more interesting this time, isn't it? We didn't just get, a sub n times sine n pi xl. We didn't just get the b sub n sitting there. We got b sub n times this other stuff. And there's even an n dependence there. Ooh, that's something. So that's going to be equal to g of x, right? This is equal to g of x. And we can do what? We can write g of x as the sum, n equals 1 to infinity of little b sub n, sine of n pi x over L, right? I can find the Fourier expansion of the initial velocity function, right? And I can, what's the formula for it? Specifically, again, just to beat a dead horse here, b sub n. We should really say beat a dead cat. Be a better saying. So 2 over L, integral from 0 to L, where were we? G of x, sine of n pi x over L. Although Travis did give me an endearing joke last time, I was happy about it. It was after you guys left, but he asked me how to make a dog. Excuse me, how to make a cat go woof. Do you guys know this one? Oh, okay. I can't really repeat it. I'll have to edit the video if I do. All right, so, but it's a great joke. So, what's that? Yeah, it's somewhat gory. Yeah. Anyway, so this is something you can calculate, right? And after you do that, what is your big B? What is big B after you do all this? Then set b sub n equal to what? The idea here is that these functions, sine of n pi x over L and sine of n pi x over L, they're linearly independent. So when you have two series with signs like this, whatever the coefficients are, they have to match up. That's the deal. So it has to be that this is that. The little b sub n I can calculate from the Fourier integrals. And so the big B sub n I calculate is simply what? It's L times little b sub n, right? Divided by what? Divided by n pi times the velocity. So you want your instructor to ask you to find the solution to the wave equation for L equal to what? What? Pi would be nice, yeah. And what speed should the strings, the wave on the string have? I mean, v equals 1 is really nice, yeah. So I probably did none of those things. But it would have been nice if I did, right? Anyway, does this, I have given you the roadmap for solving these, okay? Let me actually show you an answer, if you don't mind. Come on. Oh, so, well, not yet, I guess. I had other things I wanted to tell you, but I guess I'll wait until we're done with this math. Come on. All right, so here's one. YTT is 4yxx. So what's that mean about the speed here? Excuse me. Goodness gracious. I forget how I always forget this stupid thing. Oh, I erased it. Oh, yeah. Doesn't need our help, does he? Let's see here. How dare he? Let's see here. What's that?
Try the second side. That makes 1 over b squared equals 4.
What was the equation I wrote down but erased? I'm sorry. I just tell me what it is again. I derived it, but I forgot it already.
I was thinking that the 1 over b squared equals 4 with wings. I think that makes
No, he
b.
wants the equation. Tell me the equation.
YTT, is it YTT equals to 1 over v squared? Is it, or the other way around?
It's
First-
yxx.
first the x times the tt.
Yeah, 50-50, right? Yeah, let's see here. So what's the format we have it in? We've solved for YTT, right? So another way you could write that is YTT is equal to v squared yxx. Okay. So Zach, it's v squared is 4, right? So this is a speed 2 wave. It's a speed 2 wave equation, right? All right. And oh, look, 0 less than x less than pi. That's nice. And we're given boundary conditions, fixed boundary, fixed endpoint, right? Like we just worked out. And the initial condition is x squared times pi minus x, and the initial velocity is 0. Well, that's nice. That means that the little b sub n's are all going to be 0. Okay? That means this problem is not as annoying as another one where these are both non-zero. Your homework, test question, did I have these both non-zero? Or did I have one of these 0? Oh, I forgot. You guys haven't worked on it yet. See here. My apologies. I forgot this is engineering project week. Let's see here. Oh, yeah, there's no second page. Oh, man, I'm slipping.
Saving paper.
Saving paper. Saving paper.
And I don't believe in that, but
I definitely don't believe in that. Let's see here. The most noble purpose a tree can serve
oh, don't say that.
is to produce a piece of paper on which math is written. There is no higher calling for a tree.
I think it depends on the math.
It depends on the math.
Not to like create oxygen for us to breathe.
No.
Couldn't be that.
Math. On paper.
So I guess if the paper has numeric analysis.
If you had given me, there's a freezing family, it needs to burn the tree for firewood or something, like you'd have my attention.
Still paper.
I would think about it. But, okay, I digress a little bit. So this is speed square root of 2. Not too exciting. 0 less than x less than 1. Well, that's not as much fun. Sorry about that. Still fixed endpoints. Hooray. Man, this is kind of similar to the one I'm about to show you. And then, wait a minute. Where's my other initial condition? Come on. What? So, I'll tell you what. You can make the other one 0, all right?
You're reading the wrong one. Just the equation.
Oh! Ha ha! Ha ha! Or, all right. Yeah, so the one take-home test is more fun. But, oh man, what has happened? No. No. You want to find the atlas for the quotient of a supermanifold by the discrete submanifold? I already stuck on that once today. I don't want to. Let's go back to differential equations. No. Okay, so again, this is the initial position. Here's the initial velocity being 0. Again, for the problem that I have, thank you for saving me from reading the wrong problem. I very much appreciate that. So the one that's actually in your take-home test is a little bit different. You will have b sub n non-zero. But it might not be that bad. Those are sines and cosines. You know, it's possible if they're the right kind of sine or cosine. I don't know. I mean, There's a subclass of problems where the Fourier analysis works out really easy. You can just like look at it. It's kind of like sometimes a Calculus 2 professor will ask you to find the Taylor expansion of a polynomial. And then you're very annoyed after the test when you find out that you could have just written it down because it is its own Taylor expansion. You know, ever had that happen? Like, what is the Taylor expansion of a polynomial? It is, if the polynomial is centered already at 0 and you're asking for a Taylor's expansion at 0, it's just a polynomial again. So if I ask for like the Fourier expansion of something like, so these make decent questions for like the final because they don't involve a lot of calculation. But something like this, you know, if I had f of x was this and I asked what are the a sub n's, the answer is, well, a1 is 1, a sub 10 is 13, and all the other a's are 0. Because it's already a Fourier series, a sine series at least. Can you turn on the lights for a second? Is it better? So the point is, like, if you were to expand this as a sum of sines, there's nothing to do. It is already a sum of sines. So the Fourier coefficients are literally the 1 here, the 13 here, and all the other ones are 0. So those are decent test questions, is my point. What's not a decent test question for a 2-hour final, where everything else is going on, is to actually find the Fourier expansion of an actual function, right? Because then I'm testing your Calculus 2, which may or may not be still active. So short of us being able to put chips in your head, it's not reasonable. Current educational ethics don't allow me that. Or technology. So yeah, you can hit the lights again. Where are we? So this is my initial position, my initial velocity 0. This is my blank template solution because, oh man. Oh, I'm sorry. I was confusing in my mind your homework problem versus this problem. Your homework problem has a 2 where there's a 4 here. So your homework problem, you will not have 2. You'll have what here and here? Square root of 2. Very good. I should say take-home test. Not, I mean, it's just homework with more weight, right? Sure. And so you can calculate this integral, and if you do so, you get that. You guys can use Mathematica or Wolfram Alpha or whatever for the integration on the take-home test. That's fine with me. I'm not expecting you to work it out like gory, but I do want you to get it right. But you can, phone a friend, so to speak, with the integration. And anyway, so that gives me the a sub n. I put it in here, and there you go. That's the solution to this wave equation with that initial shape. That's how the string waves as a function of time after you let it go. Oh, here's one of those ones that I was saying would make a decent test question. See this? Here I have the same PDE, fixed endpoints, but my initial position is already Fourier expanded, right? Nice. Oh man, isn't that messed up? Look at that. I was not looking at this when I wrote this down. That's yeah, okay. And then the initial speed is 7, the sine of 5x. And so from those, I can read off that a sub, I can read from that a sub 1 is 1, a sub 4 is 13, and the others are 0. And I can also read from the, looking at the derivative, that I only have b5, there's only the b5 appearing non-trivially, so that just gives me the general solution being these things. Because I just get the b5, and what else do I get? There's something, why do I have 3 terms? I'm sorry, I'm missing something. How did I get 3 terms? I'm confused. Oh, yeah, I'm an idiot. There's 2 A's and 1 B. That's 3. Yeah, duh. All right. I actually have a picture of this one, I think, on, I think I have a plot that I can look at the solution here. Why did I just caps lock that thing? I don't know. I don't want to go to the, I don't want to go to the World Wide Web. Sorry. Stupid joke. I'm standing by it, though. No, I don't want to start graphing. I want to sign in, you doofus. Let's see here. Not you guys. Ah! Come on. All right. Just, where's... All right. Whoop, what? Let's see here. Where'd you go? Wait, here's actually, I have a solution to the... So I think this is actually the one I just looked at in the notes. And here's the motion. That's what it looks like. Those animated. So I don't know. I think it's kind of neat. Whatever. Yeah, well, part of the, I think, misleading nature of this animation is that the slider does, what the slider does is it goes over to here and then it bounces back. So, well, I guess that's not it. I don't know. No, that's not it at all. I mean, but that's time reversed at the moment, right? Time is time is counting down, but I think if you reverse the time on the wave equation, you get the same motion. But anyway. I also had this, I noticed I had this heat equation here. Why don't we look at that one? So this one, I'm not sure if we solved this one or not, but here's a very exciting solution to the heat equation. Let's make it go a little bit faster. Woo! So I guess I start out with a interesting one and then it just kind of dies. And then, again, if I could make the time not... There we go. Here, let me make it go a little bit slower. So like you're seeing the temperature start like that and then, so anyway. All right, I will stop. So in the time that remains, I was going to let you guys fill out the, and it's unfortunate there's not more of you here. I had the course evaluation form that I like to have people fill out for me. This is my in-class course evaluation form. On this form I have some things. So what I'm going to do is I'm going to give this to you guys, and could I have a volunteer to collect them at the end of class and take them to the math department for me? Danica will do it? All right.
Oh, fine, you can do it.
I don't want to do it. Why'd you raise your hand?
Now I will not look at these before the grades are already submitted and such. I'm just interested in your feedback, and this is nice that you know, if you have more to say than like 13 characters, you can write it down here. I mean, I don't know if you've noticed or not, the electronic ones, I'll be student be like, what I really liked about this course was that it was when you did the blah, blah, and that's it. It's like, what's the rest of this sentence? What did they like? I'll never know, because we can't be bothered to give you more than 50 characters in the online one. But here, you can write as much as you want. And I won't look at them until after the final. Now, the other thing I've done here is I've included some comments to help you understand the... I still do need you to do the electronic one. Please do the electronic one. That's the one that quote-unquote counts, you know. I mean, they actually count it. But I have included some important and helpful clarification on the standard questions, which I think is useful for you guys. For example, here's a small one. Instructor provided helpful feedback on assignments. I said, for example, provided solution to homework, quizzes, or tests. I mean, those are things I don't actually have to do. Just saying. This one I'm also proud of. I'd recommend this course to a friend. Assume your friend has similar life goals. This question is not asking you if someone from a non-technical major should take this. I think I went through these with you guys already, didn't I? Oh, it's such as this semester. I can't remember what I've done where, but I'm sorry, guys. But anyway, I will shut up about that, and I'm going to do is put in your quiz grades, and not with you watching, and so I'll put in the quiz grades here, and then I'll hand the quizzes back to you, okay? I guess the other thing I should probably tell you, not that it has anything to do with course evaluations, of course it doesn't, is I was thinking maybe we should have like pizza next Tuesday. What do you think?
Yes.
Yes. Is there anyone here who can get the pizza and bring it here
On Tuesday?
on Tuesday
I can do that.
from Little Caesars?
I
All right. I will fund you, of course. Do you guys like the smokehouse? Are you familiar with the smokehouse pizza? Never tried it? It's Little Caesars, but do you know about the... You never seen the commercials? Oh. It's 3 kinds of smoked meat. You've got your brisket, you've got your applewood smoked bacon, and you've got your pulled pork. And then, on pizza. And then there is like Sweet Baby Ray sauce drizzled over it. It's like the other class said it wasn't really much of a pizza, it was more of a barbecue sandwich, masquerading as a pizza. Now, if you don't like those, I can get some cheese. Who wants cheese? Nobody wants cheese? As long as it's not. I hate pineapple. Don't worry, you're safe. All my kids and wife love the pineapple pizza. So, all right. Well, I'm going to have to focus on the numbers here, and I'll shut up.